I'm Fana Boss, so hello right now. Welcome to Science Intellect Hub. Good job. Now recall that in our previous session we tried to introduce ourselves to the concept, of course, of real guesses versus the ideal guesses. And now I wanted to explore a little bit of what this concept really means, the concept of ideal. So I went to Uncle Google and asked him, hey, dear Uncle Google, what does the word ideal mean? And he said, well, as an adjective, it is satisfying one's conception of what is perfect. That's what I like. That word there is what I want, the word perfect. Waibona job. So what you'll recognize and realize is that they say the synonyms then for the concept ideal are perfect. So you wouldn't be wrong to call an ideal guess a perfect guess. Now the question is, why is this guess perfect? Well, that is because this guess is fake after all. It's impossible. It's theoretical. It's hypothetical. It's imaginary. Listen to what they say there, number 2. They say, existing only in the imagination. By Fedit and Fanabo. So, Uncle Google we Fedit also when he tried to explain to us, well, what does the concept ideal mean? Existing only in imagination. So also the concept of ideal guesses means that these ideal guesses, they must only imagine, or rather they must only be within our minds. We must only imagine them. They are not real guesses. They don't exist, Mufana boss. They are ideal. They are fake. So I like to say, Kyotava, halala right now. So they exist only in imagination. So those are the ideal guess. Why are we saying they are perfect, Ghana? We said they are perfect in such that they obey all the guess laws. It doesn't matter the temperature. It doesn't matter the pressure. That's one thing for sure. They obey all the guess laws. Do you recall something about the real guesses? The real guesses are a little bit weird. Why? Because under low temperature, you know what is happening under low temperature. They liquefy. You know what is happening under high pressure. So definitely you must know what is happening. In actual fact, these are the conditions at which the real guesses versus the ideal guesses start to deviate in terms of behavior. They start to act differently at low temperatures and high pressure. So it means something is happening at low temperature and high pressure, and you as a chemist, you must know it. So the ideal guesses, they definitely are theoretical guesses which obeys the guess laws under all conditions of temperature and pressure. So today's session is an introduction, of course, to these guess laws. We want to know, what are these guess laws then? Well, before we can even talk about these guess laws, I want us to do something. I want us to recall a very important formula here. The formula that we said PV is equals to nRT. I hope you remember that formula, whereby P is the pressure, V is the volume, N is the number of mole, the quantity of a substance, the amount of a substance, how big something is, and then R being the constant, of course, and then we have T being the temperature. And recall that we said the temperature, we always measure it in terms of Kelvins. Now, this formula here will introduce us to these different laws that these different chemists came with and about. So let's explore them. About this formula is that it has every quantity that we can be interested in about a gas. Of course, we saw the particles from University of Colorado, and we saw them colliding. So since they were colliding, it is very important to talk about pressure, the force per unit area. As those particles were colliding, there were forces exerted. It's like when you are in a game, of course, playing soccer, and then it happens that La Tulana does. Of course, you are tulaning with a force. So as you tulana, there's a particular force that, of course, is going to be exerted between you. So is the same thing with particles. As they collide, there are forces due to those collisions. It is important to talk about pressure. It is important to talk about volume. Remember, we said that gases have a tendency of filling the container. So we must know how small or big is the container. We must know the volume of the container. Well, we are talking about gases. Gases are, of course, matter. Matter is anything that has mass and occupies space. So definitely it will make sense to talk about the amount of a substance. It will be very important to talk about the amount of gas then that we have. That way then we can be saying, well, we are interested in gases. Then there is this R, which will make calculations very convenient. And then we have temperature. We saw the influence of temperature to the particles, and we saw what behavior those particles ended up on because of the increase or decrease in temperature. So temperature is a very, very important thing then. But what I want to discuss with you at this time, a moment, what if then we are having R as a constant, because that's what we have, R is a constant. But we are saying, what if then we also keep the amount of gas constant? We keep the temperature constant. We do not change the temperature. We do not change the amount of a substance. We keep those constant. And we want to see then the changes only between the pressure and the volume. Those are the only changes that we are interested in. Pressure and volume. So now, every time, of course, we see a constant, as mathematicians, we may know that, okay, we can put 1 there. So here we will have PV is equals to 1. Why 1? Because N is constant, R is constant, T is constant. All of them are constants. Now let's put 1 in their place. And let's divide both sides perhaps by V and see what's going to happen. We are going to end up with pressure is equals to 1 over V. That is the relationship that, of course, this chemist here was interested in. So I'm talking about Boyle's here. So Boyle's law, of course, as one of the gas laws, is only interested in the relationship between pressure and volume. So let us explore a little bit about Boyle's law. But what we can recognize already is that we are having P as a numerator, we are having V as a denominator. And I've recognized something. Every time you are looking at a relationship between a numerator and a denominator, that is an inversely proportional relationship. But we'll try to explore that right now. What we have there, of course, we have the pressure. Look at the pressure, it's relatively low. We have the volume greater. But now we try to decrease the volume. Look at what has happened to the pressure. It has increased. That is because pressure is inversely proportional to volume. So, good job. Right now. Bazobuza nge-exam mfanaboso. Njalo nje. Right now. So here they give us a question and they say an investigation was done to determine the relationship. Of course, we are looking at the relationship between the following. Let's see the relationship between what and what. We were looking at the relationship, of course, between pressure and volume. That's what we were looking at. Of course, of a fixed mass of gas. So when we say the mass was fixed, we already understand that also the temperature was fixed. So we were looking now, or we are looking now, only at the relationship between the pressure and the volume. The table below shows the results of the investigation. So we are given pressure in kilopascals, we are given volume in centimeter cubed. Now I want you to look at the trend of the numbers, of course, under pressure there. You start with 25, you go to 12,5, you go to 6,25. You can see that as you go down, what is happening is that there is a decrease in terms of the pressure. So we can say, well, the pressure is decreasing as we go down. But what about the volume? Look at the volume. It starts at 5, it goes to 10, 20, 25, 30. So what we see is that it is definitely increasing. So as we go this way, it is increasing. So here we can write decrease. Here then we will write what? We will write increase. That is the relationship that Boyle spoke of and about in Fanaboso. To say as there is a decrease in pressure, there is an increase in volume. Wayibona taba mfana boss. Question 6.1 says, use the results to draw a graph of volume versus pressure. You just have to understand which one should be the dependent variable, which one should be the independent variable. For our graph here, we will take the dependent variable as being the volume, and then the independent variable being what? Being the pressure. So this is the table that we are going to see here, mfana boso. Wayibona tab. We can see that, okay, what was happening here is that this side, of course, we are having what? This side we are having the pressure, or rather we are having the volume, and then this side we are having the pressure. What is the volume? The volume, if you can check there, is 35, and then the volume is 35 when obviously the pressure is 3,5. You can agree with me, along there we have 3,5. So the pressure 3,5, the corresponding volume is definitely 35. Wayibona tab. Then we ask ourselves then, what happens when our pressure is 4,2? The pressure is 4,2 just there after the 3,5. We have 4,2, of course. Therefore, that will be what? That will be the corresponding volume, which is 30. Kanjalo. So this is how, of course, you are gonna plot this graph here. Wayibona tab. But remember, you are a chemist. You must always give what? You must always give the title of your graph. This will be the graph of pressure versus volume. Wayibona tab mfana boso. There is the volume, there is the pressure. Now, what do you recognize about their relationship? Look at what is happening, and what is happening to the numbers when we are talking about volume here. What is happening to the numbers as we go down from 35, 30, 25, 20, 15, kanjalo. It means you can see that the numbers are going down, but on the horizontal line, which is of pressure, we can see that we are having 5, 10, 15. They are what? They are increasing. So we are having an increase this side, we are having a decrease that side. Wayibona tab. That is the relationship that Boyle spoke of and about mfana boso. Boyle's law, the relationship between pressure and volume. So that is, of course, 6.1. We must have the ability to draw that graph there. It looks horrible, but I hope yours will look better. Question 6.2 says, which law? Remember that there are various laws that we are going to learn of and about, but here we are asking ourselves a question, which is, which law describes the relationship between pressure and volume of a fixed amount of gas? So that will be very simple to answer, because we know that it is definitely no one else but Boyle, with his law, Boyle's law. Let's explore question 6.3. They say, calculate the volume of the gas in centimeter cubed. If the pressure exerted on the gas is 35 kilopascals. Wow, that sounds sophisticated. But what we'll recognize from Boyle's law, as much as we said pressure is inversely proportional to volume, what we are saying then is to say, okay, so what we will have as an equation will be something that looks like this. P1 V1 is equals to, of course, P2 V2. Pressure, V, of course, being volume. So we have P1 V1, P2 V2. So what we are going to do then, in actual fact, what I would like you to do is to multiply 25 by 5, 12,5 by 10, 6,25 by 20, kanjalo, and see what is happening. Just try it and see what is happening. Wayibona tab. But what we're going to do then, we're going to take any among these. We can take the first one to be P1, and of course this will be our V1. So already we have P1, we have V1. We will have here 25 multiplied by what? Multiplied by 5, which is equals to P2. P2 is given here. This is going to be our P2 then, 35. Multiplied by V2. V2 is what we will be looking for. Wayibona tab. So you can perform the mathematics there. You are going to end up with 125 is equals to 35 V2. multiplied by V2 rather. So you can divide by 35 on both sides, and then you are going to get that, well, V2 is equals to what? V2 is equals to 3,57 centimeter cubed. So, halala, right now. We use P1 V1 is equals to P2 V2 for Boyle's law, whereby obviously the pressure is inversely proportional to the volume. Halala, right now. Now when we go and see 6.4 is a question I always say, zange exam mfana boss njalo nje. Here they say, write down 2 conditions under which the gas will do what? The gas will behave like an ideal gas. What am I saying? They say write down 2 conditions under which the gas used will behave like an ideal gas. When do they behave the same? We know that they do behave the same at high temperatures and of course what? And of course low pressures. The ideal gas and the real gases behave the same. So what is happening here is that of course the gas that we were exploring here was in actual fact a real gas. So when does this real gas behave like an ideal gas? Well, at these conditions: high temperature, low pressure. Another question they might ask is, when do their behavior deviate? You must know that mfana boss. So it is at low temperature, high pressure. Mfana boss. So hello, right now. My name is Mr. Mjaki Sanese. They call me Mr. M Mfana boss. So halala, right now. So in the next session, we will of course try to focus on the other 2 laws, which is Gay-Lussac as well as Charles' law. And then of course we will consolidate the ideal gas laws and make sure that we are done with this concept. For those who did not watch the previous session, please go and watch the previous session, because these concepts, they follow one another. It is a playlist. I called it Ideal Gases, grade 11. Halala, right now, till we meet on the next session. Blind fun boss.